Okay, so we are going to look at a problem with uniform circular motion, another practice problem. And this one says you, with mass of 75 kilograms, are driving down a road when you approach a small hill. The hill is like part of a circle with radius 35 meters. When you go over the hill, you feel a little lighter, right? When we think about going over a hill on the country road, we kind of get that funny feeling in our tummy. We feel a little light. All right, so let's imagine that we were sitting on a scale when we were going over the hill. Would the scale read less than your weight? Is this feeling of lightness actually manifest itself in the reading on a scale? So we're going to imagine that we are going 15 meters per second, and we are going to analyze the reading on the scale, and then we'll compare it to our weight. Okay, so let me share my screen with you. We'll do this as a practice problem. Oh, there we go. All right, so you have a mass of 75 kilograms, the problem stated. And it's stated that you're going to go over this bump in the road at 15 meters per second, and the radius of that bump is 35 meters. So what does that look like? So let's imagine here's our road, and here you are at the top of the bump in your car. And this is what we mean by the radius of 35 meters. So as we approach the apex of this hill, it's as if we're in a circle going that speed, but that circle has a radius of 35 meters. Okay, so that's sort of the picture to visualize. Now we're going to analyze the forces on you. So let's remember what sort of forces act on you. Well, you have mass. So the force of gravity between you and the earth. And remember, you're sitting on that scale. So there's the force of the scale, which because you're sitting on it, it's that squishy force. And that's what we call the normal force. So that's between you and the scale. All right. There's no other forces acting on you. Okay, so those are the only two things you're interacting with. So those are the only two forces that are going to show up in our free body diagram. So we know that the force of gravity acts down, and we know that the normal force acts in the upward direction at this location. Okay, so there's no horizontal forces, so we really only have to analyze the vertical components. So force 1 and force 2. Force 1 is negative, and we know that's equal to mg. It's pointing in the downward direction. Force 2 is positive. It's pointing in the upward direction. So we're going to analyze the sum of the forces vertically. Now, oftentimes when we do motion analysis, especially on a horizontal plane, the sum of the forces vertically is 0. But is it in this case? If we're moving around this circle, even though we're only transversing a small portion of it, it's changing its motion, it's changing its direction. So what is the direction of that force? Well, it would be downward. If this is uniform circular motion, remember the direction of the centripetal acceleration, and thus the force is always towards the center. And towards the center here is in the downward direction. So that's the direction of the force, which is vertical. So there is indeed a vertical acceleration. Now we ask ourselves, is this translational motion or circular motion? And because it's circular motion, this is the centripetal acceleration. So the vertical forces are what are giving rise to the circular motion. All right, which is a good thing because there aren't any other forces acting. So we have N minus mg is going to equal to our mass times our centripetal acceleration. So what's the reading on the scale, which is what we were interested in? Well, that's our normal force. And our normal force is equal to the mass times the centripetal acceleration plus the mass times gravity. Now, the second thing that we need to ask ourselves is, do these directions make sense? We said that the force of gravity is going to be pointing in the downward direction. We also said that the acceleration is in the downward direction because we're at the top of the hill. So we want to make sure we're careful in our analysis and we recognize that that acceleration is negative. So I missed that up here, I apologize. But as I looked at this relationship, I knew that there was something wrong about this. That acceleration had to be negative because the direction is in the downward direction. All right, so we have the normal force. I'm just gonna flip-flop these so they look more like equations we're used to seeing, is equal to the mass times gravity minus the mass times the centripetal acceleration. So let's put in our numbers. We have n equals 75 times 9.8 minus 75 times v squared over r. And I left that as a variable so you were reminded that it's the centripetal acceleration. Move that up for you a little bit. And so we have n is equal to 75 times 9.8, which is 735, minus 75 times 15 squared, all over 35. And that is n is equal to 735 minus 482. And so this reading on the scale is going to be 252.9 newtons, much less than the force of gravity, which was our 735. So that feeling of lightness sure is a feeling of lightness. As we talk about the feeling we feel is really how we are interacting with that scale. Okay, so recognizing, just going back up here, recognizing that we are in circular motion, that the forces interacting on the object, U, what they are, and our free body diagram. So that's standard kind of practice. We want to recognize the direction of that acceleration is vertical. And so our vertical forces are the source of that acceleration. And because we're in circular motion, that source is a centripetal acceleration. Recognizing that we do have to be careful about the direction of our acceleration as we continue to solve a problem. Because our acceleration is pointing down, we need to make sure that it's represented properly in the sum of the forces. And then solving for what we're interested in. All right, so uniform circular motion, sort of in one dimension. We'll always look at the circular motion either horizontally or vertically. And then following our forces process and recognizing when we are in that circular motion. Okay, good job.